Yes. Yes. What he has to say, he doesn't take care of class for the whole growing, so at home. Speak to us. Yeah.
Hello, morning. Here. And we have one more homework mandatorily due, and the other one is optional. Both due next week. First is due on Monday. And the final exam will include about 40% of topics after midterm 3, which means the rest of it would be before midterm 3 or anywhere in between. I expect there will be about 10 questions, even though we have had 7 or 8 questions during the normal exam. We will have about 2 hours, significantly more than double the time, but still the questions may not double. It will be about 1.5 times. So, any questions related to midterm or in general what to expect going forward? Okay. I will also finish a little early today. I would like to do the evaluations for this course. So I'll need a volunteer who will take care of that. So someone has to distribute it, pick it up, and return it to the physics office, which is right on the floor. If you come from the doors behind this room, if you keep walking about maybe 20 meters or so, you see the physics office, and the room number is written on this. It has to be someone among you. I cannot do that. That's the requirement, that evaluations are not taken care of by me. If someone could volunteer, that would be good. Yeah, thank you. So just if you could remind me 10 minutes before the class, I'll finish. And if you could do that. Thank you very much. Yeah. We were studying refraction. I should turn the camera before I forget. I think last time it was completely off. Refraction is a phenomena that happens at the interface of two optical mediums. By optical medium, I mean anything in which the speed of light changes from speed of light in vacuum. Whenever we talk about nothing can go faster than speed of light, we mean speed of light in vacuum. So speed of light can be slowed down, or it does slow down in every medium, which means that gives you a room between the slowed down speed of light in the medium and the speed of light itself. And something could go faster than speed of light in principle there. And that does happen in the context of sound. If you notice sound speed, which is entirely different from light, it behaves differently. But there is a very relevant phenomena there, that speed of sound is 320 meters per second, which is about 650 miles per hour. And you can ask, what will happen if something goes faster than speed of sound? And there are things that do go faster than speed of sound. Classic example are fighter jets. Fighter jets can go easily about 1,000 miles per hour. And when they go, you will notice that you will hear the sound that the jet makes after the jet has crossed you. So the sound reaches after you because the jet is faster than the sound. And in that kind of phenomena, the energy propagation does not happen as usually it happens in the normal mediums. And it happens in the shape of a cone. And all the energy is concentrated on the boundary of the cone. And when that energy strikes you, it could be significantly high in energy, and significant enough that it can break glasses. So if you have ever lived close to a runway, especially a military base, you will notice that your windows could get shattered just because an airplane is flying close to you. So those are called shock waves. Similar things can happen in light. I'm just mentioning it. We won't be discussing that often. We will be talking about simple situations where light or things are going slower than the speed of light in that medium. We talked about the medium property described by the refractive index, which is the speed of light in vacuum. So this is the speed of light in vacuum divided by the speed of light in the medium. And if this is smaller, that means that the refractive index will always be greater than 1. So this quantity is always greater than or equal to 1. This is called the refractive index. Even though it seems like we have introduced it as the speed or the ratio of speeds, it is basically the electrical and magnetic properties of the medium that decides this property, because eventually the speed of light is decided by how electric field and magnetic field propagates in the medium. So this is an electrical, so this is primarily decided by electrical property, but just to give it theoretically, the correct explanation is electric plus magnetic. Both decided, but magnetic property is significantly smaller, about 1,000 times smaller than the electric response. So that is a magnetic response and an electric response, but the magnetic response is significantly smaller. So it is the electrical properties that decide it. More precisely, it is called the dielectric property of the material. For our purposes, we are simply interested in the refractive index, and we introduce the idea of law of refraction, what it governs. Law of refraction says that at any interface, if you have two interfaces which is described by this refractive index, you have n1 sine theta 1 is equal to n2 sine theta 2. This is also called the Snell's law. That's just another name, and it is often referred to as the Snell's law 2. How does this look like? We have two situations possible. We could have a light going from air to water, and air is 1.0 to 2 significant digits, and water is 1.3. So let's say this is N1 is equal to 1.0 and N2 is equal to 1.3. If the light originates from in the first medium, so that's your light, we draw a normal line. Angles are always referred to the normal line, not with respect to the surface. So that's your angle θ1. And instead of going straight down in here, it will bend towards the, oh, so that's θ2. So since N2 increased, θ2 has to decrease. N2 increased, θ2 has to decrease. Sine of θ2, even though it is not linear, it is monotonically increasing. So for our purposes, at least for analysis, you can say that this is linear. So if this N2 increases, and if you want to keep this constant, then θ2 has to decrease. So since N2 has increased from 1 to 1.3, θ2 has to compensate for that, and that decreases. You could have another situation where you have N1 to be about 1. Let's say 1.8, and N2 to be 1.3, again water. This is the situation for benzene, and this could be water. Just an example where the refractive index is larger. And again, let us say light comes and falls at the interface. That's your normal line. That's θ1. And light would have like to go all the way straight without deviating. If the interface was not there, it would have gone straight. But now N2 relative to N1, N2 has decreased, so the angle has to increase. So this bends away from the norm. That's your angle θ2. And projecting these rays backward is how things look like. So if there was someone standing here, this light ray when propagated backward, that person will look smaller or shorter relative to someone inside the second medium. So that was your original height, and it will look shorter as perceived by an eye here. Same thing in here, if you were to project this line backward, this is your original height, and the person looks taller, right? Taller by that much amount. And if you're in water, that means fishes see you significantly bigger when they are looking at you. Notice that I said sine function is, even though not linear, it is monotonically increasing. But we also know that sine function has a maximum value, right? Sine function has a maximum value of 1. And one could ask, what does that play a role? What if when I take the quantities on the other side, is it possible that we could have a scenario where this goes greater than 1? And what could happen in that case? And what is the physical scenario associated with this? So this is called the total internal reflection. Total internal reflection. It's a very relatively simple concept, comes out of refraction almost immediately, but the technology based on this has been used so much that almost all the communications that we have, for example, when we think of internet communication, we intuitively always think that there are satellites involved, right? The signal goes to the satellite and it goes into another country. But you'll be surprised to know that almost 99% of the communication does not go through air. It goes through fiber, glass wires that are built out of almost glass, and they are little flexible and they go underneath the ocean. It is much faster or much more efficient. It's not faster significantly. It is efficient in the sense when signal is going through a wire, it could lose some of its energy. When you're sending something into the satellite, you have to radiate something in all directions. Like you don't have the control of going along a wire. So you have to spend too much energy, and most of the energy is lost in radiating in all directions when you send it through satellite. And by the time it reaches the satellite, there is a very significantly small amount of energy it reaches, and you need to have a detector, which is very expensive to pick up that small amount of energy. So satellites are not the best ways of communication, or not necessarily the best ways of communication. If you want a more efficient way, you simply send it through a wire, but this time not a conducting wire. Again, conducting wires are expensive. It's built, usually conductors are aluminum, silver and gold, but instead you simply use glass. And how do you pass signal through glass? So that's the concept in here. So let's talk about a situation. Again, exactly the same idea. For now, we simply have one interface, and then we will make it, we'll talk about how it passes through a cylindrical wire. So we have an interface like this, and let's say we have an air, right? So this is air, and this could be water, or let's say glass. And this is 1.5, and that's 1.0. We do know that if light goes from the second medium to the first medium, because air is rarer compared to glass, so light rays, if you originating from glass, has to bend away from the normal, right? Instead of going straight, they bend away from the normal. That's reasonable. But now, so this is the first ray, that's the first ray. Increase the incident angle a little, and because the sine function does not go linearly, this will increase a little more than how much you have increased in here. So that's down here. So that's your 1, so that's your 2, so that's a second ray. Keep increasing, and it is not too hard to imagine that there is a limit beyond which there is no room for the second third angle. So this, the third ray here, pretty much grazes through the interface, and beyond that angle, there is no light cannot enter the surface. It has to reflect back. Every time light comes, two things happen. Some of it reflects, and some of it transmits through the material. But any ray that is beyond 3, so let's call it 4 doesn't enter this into the medium at all. So from this point to this point, all the light has to reflect back. So that is a critical value here. So this is the critical value, theta C, for which this is 90 degrees. The refracted angle is exactly 90 degrees. That means that beyond that angle, you cannot have refraction between these two interfaces. Let's calculate this critical angle for the material, for the interface involving air and glass, and we learned that it is 1.5 times sine of this critical angle is equal to, after refraction, the angle now is sine of 90 degrees. And the refractive index is simply 1. We're talking about air in this case. So this is equal to 1, and your equation becomes sine of theta C is 1.0 divided by 1.5. This means the critical angle is equal to 0.5, and that's about 42 degrees. That's a lot of room there. Notice there is almost 48 degrees remaining, right? If you think of 90 degree as the open window possible for the rays to come, more than half of the angles are not available for refraction when you think of it. If you were to extend this further to a larger, a material that has a larger refractive index, it is easy to notice that if you have diamond, which has a refractive index of 2.4, in that case, the critical angle comes out to be sine inverse between diamond and air. It is 1.0 over 2.4, and that's equal to 25 degrees. And that means 65 degrees is not available. Out of 90 degrees, 65 degrees is not available for refraction. Refraction means light cannot enter for entering the diamond, which means most of the light is going to reflect back, and that's why diamond sparkles. That's why diamond is so much more reflecting than normal glass material, and that's the property of diamond, or that's the interesting part in it. How can we use this for technology? Convert some signal, electrical signals, into light signals, and it is easy to see that if you had a cylindrical glass material, think of this as glass. So this is glass, air, and air. If the light comes within a certain angle, let's say it enters the glass and beyond this, so this is not available. But once it is in that region, if you make sure that all the signal is confined within this region, so this is also not available. So that's your signal. Signal is confined into light coming inside a cone, and from this point on, it cannot reflect or refract out, so it has to reflect. If it cannot refract, it will reflect, and once it comes here, because these two are parallel, again it has met the conditions that it cannot go out, and it gets stuck. So light, if you make sure that light does not have more than a certain amount of incident angle while coming into the glass material, it gets stuck here, and it has to keep reflecting off and on inside that glass material, and it comes out from this side. If this was very long, in fact, these days you can, or it was realized that by putting in some amount of plastic inside the glass, you can actually make this flexible, and you have what is called a fiber optic. This is called a fiber optic cable. You might have heard of this when you're deciding on an internet service. Many of the internet services use fiber optic cables. That means they're not using metals to pass the signal. They're using glass. Glass are these days, these are materials where you mix up plastic with it, but they have all the properties of glass. The refractive index is of the order of about 1.5, and you can actually make this flexible, go around the house, or for that matter, go go under the Atlantic Ocean, and the signal goes from one continent to the other. And most of the signals between the continents, most of the communication signals between the continent, 99% of them use fiber optic cable, not metallic wires, just because it is significantly cheaper and also because it is significantly more efficient. Having talked about total internal reflection, now we want to concentrate on spherical lenses this time. Earlier we talked about spherical mirrors, and as I said, in the case of mirror, we will surely have a question on spherical lens and one question on spherical mirror. In that sense, you at least have 2 questions sure in the final exam. What exactly will be the question is going to be different, but surely on that. And if you notice, if you look up, just glance through all the old final exams, the format of the question is exactly the same. It's just I changed the focal length and where the object is kept. So we should talk about lenses, and we use lenses all the time. For example, for corrective glasses for your eyes, that uses lenses. So let's talk about spherical lenses. And like in mirrors, we can have a lot of situations, but configurations, we will talk about only spherical surfaces or interfaces. Spherical lenses, we will talk about 2 types of spherical lenses. There are lots of possibilities in here. Talk about convex lens. And the second, we will talk about concave lens. A convex lens has the shape that if you have light coming from one side, always we draw an optical axis. So that's your optical axis, and the arrow tells that light is going from left to right as pictured. Then vex means it is not concave, so it is the bulged out portion where the light is hitting is the bulged out portion and not the cave side. Concave lens, on the other hand, will look like this. Notice the cave side is in the side where the light is coming and hitting is actually the cave side. In principle, we are talking about interfaces where these are spherical, right? These are spherical, and we notice that a lens is formed out of 2 surfaces. Right? There is one circle here, and there is another circle there. In mirrors, there was only one sphere that was necessary. You take a section out of the sphere and you get a mirror. So that immediately leads to the idea that these 2 circles do not have to have the same radius. In fact, you do not even have to have this intersecting. You can have, this is convex, but this could be concave. So that's also a lens. Like both are concave ended, but it's just that their radius of curvature is different. But we won't talk about those situations. We will make things very simple here. Whenever we talk about convex lens, we will say this is symmetric in the sense that both the radius of curvature is the same. Same thing here, concave. We will say both the radius of curvature is the same. It is symmetric about that line. How can we understand how light behaves in these lenses? A good approximation is, let's see what light is trying to do. Replace this with triangles. That's an approximation. And when light goes through a triangle, let's have a ray of light going in here. There is a normal line in this manner. If this is air and if this was glass, light will try to bend a little. So So that's bent. And then when it is tried to come from a denser medium to rarer medium, it again tries to bend, but this time it again does the same direction here. So it tries to bend this way. So what is happening is that it has curved down. So overall, this is equivalent to saying, for our purposes, this was just an approximation. As far as convex lens goes, light that is coming in, let's pretend that it is coming parallel to the axis. It will go through a point which is a focal point. So that's your parallel rays coming in. They converge at this point. So this is called a converging lens. Notice I didn't have to remember this. I can use the idea of a triangle. Light comes in and it will, just because of the shape of this, it will try to bend and converge into one point. So a convex lens converges light towards a point, towards the focal length, and so it's called a converging lens. Same thing if we were to try to do with concave lens. Now, this time the triangle is inverted. So this was two triangles if you want. This could have been this manner, right? Symmetrically speaking, up and down behaves the same way. This time the triangle is inverted. It looks like this. This is the extreme version of a concave lens. And now again, bring in light in here. It will bend this way. And it will bend a little more on the other side because it's going from rarer to denser, and while going out, it's going from denser to rarer. It goes the opposite way, both direction. And if you notice, we can immediately conclude that in the concave lens, if you have parallel rays coming in, they will diverge out. That's the diverging part. But then when it is diverging, it seems to be coming out of a point, right? If you were to project it backward, they seem to be coming out of a point. And that's called the focal length. So this is a diverging lens. That means to say that if you were to look through this, so usually you're looking from the other side, that's not necessary. But if you were to look from the other side, light seems to be diverging out of a concave lens. For these purposes, we will change our mirror formula will exactly be the same as the lens formula, but we will change our sign conventions here. And next time we will go over all the possible images that can be formed here. At this point, so it's 15 minutes left. I'll stop here so that you can do the evaluations for this course. The information you will need is, Sandra, you can distribute this and I'll write down the information.
That's crazy. Thanks.